Welcome to video 6.3 in our first Principles of Astrophotography series. In this video we discuss chromatic aberration, which is the main reason why high-end refracting telescopes have so many lenses.
Yeah. So Newtonian reflectors don't suffer from chromatic aberration because they don't have any lenses?
That's correct.
It's not corrected. It's correct, but it's not corrected for
chromatic aberration. Good point. Yeah.
Because it has none.
Yeah, so they've got, a Newtonian reflector, light comes in through the front of the telescope, bounces off of a parabolic mirror, and that doesn't introduce any chromatic aberration, bounces off a diagonal mirror, and then into your either eyepiece or your camera. So if you're looking through an eyepiece, then there could be some chromatic aberration introduced by the eyepiece, but the bottom line is that you've got to pass through glass in order to get chromatic aberration.
Yeah.
So that's why Newtonian reflectors give you your biggest aperture bang for the buck. If you want to get a lot of aperture and clear image and clean images, Newtonian reflector is the cheapest option for you.
They're not the only option, though.
No.
Yeah.
This video is based on section 3.6.3 of our First Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 48, dispersion. This is a little bit reviewy, but dispersion is the wavelength dependence of the speed of light in a medium or through a medium.
And it's not even a little bit reviewy, it is reviewy of a principle that we talked about in video 4.2. We talked about the fact that light travels more slowly through a medium like glass or water or even air than it does through vacuum, which is the absence of any material. But this has important consequences for chromatic aberration.
All right, 98, prism dispersion. Different colors are deflected by a prism at different angles. Well, I think we've all seen this.
I think we have in the Pink Floyd album.
Yeah.
Or maybe we've seen it in real life or in a demonstration, but it's really quite spectacular. And even this happens with the chandelier. The little cut glass in chandeliers provides the prisms that causes this chromatic aberration. You can see the different colors against
so cool.
Against the wall. So as you can see here in this diagram, the red gets deflected the least, and the blue and violet gets diverted or refracted the most.
Yeah.
So here's the original direction of the light before it hit the prism. The red gets deflected the least and the blue the most.
Principle 99. Could you believe we got to 99?
We're at 99.
99.
Out of 153.
Great. Chromatic aberration. Different colors come to focus at different distances from a lens.
So we're talking about passing through a lens. We're talking about the speed of light through that lens depends on the wavelength. And because the speed of light depends on the wavelength, that's dispersion, the angles that it's bent, the light is bent, depends on the wavelength. So if you have light coming in, red, green, and blue, then the different wavelengths travel at different speeds, they have different indices of refraction, and they bend more or less. The red bends or gets deflected the least, and the blue gets deflected the most. What does that say? It says that for blue light, the focal length is here. Whereas for red, focal length is larger. That's minorly embarrassing because that means that through a single lens, if you focus the blue light so it's right in focus, so you can pinpoint images of blue stars in your image plane, then your red stars are going to be out of focus.
Fat and blobby.
And vice versa. If you focus the red stars to the green, then the other colors are going to be out of focus. So that's really embarrassing. So what telescope manufacturers do is they use several lenses with different refractive indices. So they use fluorite glass or SD or ED glasses. There are different glasses that are used instead of the regular glass that you see in your windows, and with different configurations in order to reduce as much as possible that chromatic aberration. So this is for the CAT 91 WIFD telescope, which has 5 lenses that are precisely ground and precisely calculated to bring all wavelengths as much as possible to focus at the same distance over the entire field of view. So that's a big job.
This breaks my brain though, because every time you introduce something else, it's going to mess up another thing or focal. It's going to be.
I haven't ever looked at the codes that they must use to design these bad boys.
It's got to be crazy.
But you know, every little angle at each different spot in each lens has to be just right to do it. So it's really miraculous. I mean, we live in a great day.
Yeah.
I mean, when I was growing up, people had, I mean, the telescope that I had when I was 12, I think it was just a singlet, meaning a single lens. And then they came out with doublets and then triplets, so 3 lenses. And now today we have quadruplets or quintuplets or sometimes septuplets and just tons of lenses to get more and more correction.
And the extra lenses are not for your focal length, or they are to correct and make sure that the point coming in is the point we get out.
So to create a one-to-one correspondence like we talked about before between points in the field of view and points on the image, but with all of the colors coming to focus at the same place.
Right.
Yeah.
So this is where it's hard when trying to look at a telescope. Is you look at the doublet and you say, well, the price is way better than the triplet, but then you're and me as a new astrophotographer says, well, the images look great from the doublet and it's cheaper and let's just go for it. But then you realize that you cannot fix the chromatic aberration that you could have with a triplet with a doublet. You just can't. So there's.
As I remember, oh, sorry, go ahead.
Yeah, so, I was just wondering, where is the point? I want to know where the point is, where my money spent and the number of elements is
where's the crossover
where's
point?
the crossover?
Yeah, so as I remember, the triplets, when they first came out, the whole goal of a triplet, since you have 3 lenses and 3 colors, red, green, and blue, you want to bring all 3 colors to the focus of the same point.
Yeah.
But red isn't a single color. It's a range of wavelengths, and same with green and same with blue. So you're going to be out of focus a little bit somewhere between red and green, and
we're dealing with broadband light.
Yeah, and so it's but a lot of these do a really, really good job, and you can look at spot diagrams, which we talked about in some of our other videos, like review videos.
Yeah.
But to show how well the design of the 5-element design or the 3-element design will focus light of all different kinds of colors. But we should say that spot diagrams, those are theoretical calculations. Those aren't, if you don't build that telescope with the figure, the curvature of all the surfaces exactly right and put them in exactly the right spots, then you're not going to be able to replicate those spot diagrams. But.
And you'll find this even in normal like camera and lens reviewers. They look at chromatic aberration, but very few know why chromatic aberration happens. That it's because the light is refracted differently depending on the wavelength.
That's right.
So, like, this is really basic but important, especially in astrophotography.
Especially, and I was going to say something about that too. With visual observing with my little 60 millimeter telescope I had when I was 12, you could see Jupiter just fine. It was fine, right? Looking with your eye. But if you want a flat image plane with all colors coming to the focus at the same distance at all points on the plane, then like what you need for an image of an extended object. I mean, Jupiter is no big deal because it's so tiny, and you can look at it right through the center of the optical train, and you can get a pretty good image. But yeah, so that's for the gurus, optical engineers in this that have done some wizardry, and a lot of the telescope manufacturers are coming up with amazing, innovative designs. We just ordered a SQA 55.
I'm so excited.
Yeah, we're excited about that. We needed for my trip to Peru, we needed a
For row. We need row.
Yeah. We needed a really wide field telescope. So we're excited about that one. But that one, according to reviews by Lucamatico, and I think Trevor did one of Astro Backyard, and Quiv did one of Quiv the Lazy Geek, that does a really good job for a wide field scope for chromatic aberration. Thanks so much for watching.
And we'll see you next time.